Thank you for attending my presentation on next generation computing. To start off, we have Moore's Law. Moore's Law states that the number of transistors on a computer's chip doubles every 18 to 24 months. Moore's Law has been proven to push the semiconductor industry forward about 40 years. Moore's Law has allowed for the scaling down of complementary metal oxide semiconductors to produce high-speed, low-size, and low-power, high-density devices with low production costs. But there are problems that have been caused by Moore's Law. The main ones are static power issues, tiny transistors leaks, electricities even when they aren't switching, and dynamic power issues where more data movement and longer wiring paths cause more energy use and heat. Here's a graph showing Moore's Law and its impact. It's still unclear what technology will eventually use to replace CMOS. The problem is that the hardware isn't the only factor that needs to be considered, as other factors such as these have to be considered in future developments. New computer architectures, new programming models, new software, and new user interfaces. This is a table showing some criteria that needs to be followed for future devices. Non-volatility, the ability to store data even when power is off, ideally with memory built in. Efficient logic operations, logic that can be done more efficiently, for example using analog methods. Regular or organized structures, or regular repeatable layout style, which is used in quantum cellular automata. Self-adaptive behavior, devices that can adjust or tune themselves, coherent or collective behaviors, and groups of devices working together in a way that gives low power switching, high reliability, or other shared advantages. One major challenge in advancing beyond CMOS is the wide variety of new technologies and computer architectures that are currently being explored. Some new computing ideas are designed only for specific applications, while others are meant to be general purpose like today's CPUs. Even with these challenges, there are real opportunities for progress, and the focus of technology is shifting from simply shrinking transistors to creating new functionings and new types of applications. This is a cluster map showing relevant groups that have been studied throughout the years. However, the groups that we will go in more detail on are biocomputing, nanocomputing, spintropics, and optical and photonic computing. And here is a map of those 4 topics. To start off, we have biocomputing. Biocomputing covers many types of computing methods inspired by how biological systems work. Biocomputing aims to use ideas and mechanisms from biological systems to create a new way of processing information. It draws inspiration from how these living organisms sense, store, and react to information, and applies these principles to computing methods like DNA computing, neural modes, and swarm algorithms. Membrane computing investigates the class of computing known as membrane systems or P-systems, which are abstracted from the architecture's structure functioning of biological membranes such as living cells, tissues, and organs. Membrane computing focuses on how cells are divided into different sections by membranes. It's a theory used to describe how systems that work in parallel in each other. It gives rules on how many parts of systems can work at the same time. Scientists use membrane computing in biology to model things like how photosynthesis works, how cells send signals to each other, and how immune systems respond to threats. Computing scientists also use membrane computing in areas such as computing graphics, cryptography, and solving difficult computational problems. Membrane-based computing models are very powerful, and they can do what traditional computers' tuning model can do. They are very efficient for certain problems. Some problems that normally take computers extremely long time can be solved much faster in a reasonable practical time using these models. The P-system was created in 1998 by Jorge Juan from the Romanian Academy. Since then, research on P-systems have grown quickly. There are three kinds of main P-systems: cell-like P-systems, which are used structures of single cell; tissue-like P-systems, which are based on groups of cells working together; neural-like P-systems, inspired how neurons work. This group also includes spiking neutral P-systems. Now we move on to DNA molecule computing, also known as biomolecular computing. It is based on the idea that information can be stored in biological molecules such as DNA or RNA of electronic circuits. These molecules can be manipulated using lab techniques to perform math logic operations like a computer does. This is different from membrane computing, cellular automata, or evolution computing, which is theoretical logic. DNA computing also uses molecules as hardware. DNA is all used in input and DNA-based logic circuits to build complex systems that are programmable, precise, and efficient. Different ways to go about DNA computing include DNA strands, DNA hairpins, and DNA enzymes. DNA computing has contributed significantly to nanoscience by providing computational insights into key scientific questions and by helping researchers understand self-assembly processes in molecules. Here are some advantages of DNA computing. DNA can store much more data than traditional silicon-based computers. DNA operations are massively parallel. Because of this parallelism, DNA computing is ideal for solving fuzzy logic questions and generating billions of possible answers simultaneously. DNA computers handle huge amounts of memory efficiently and are inexpensive to build. Here are some problems, however, with DNA computing. Some problems, even simpler ones, may require impractically large amounts of DNA. Key details like error rates, coding methods, and performing certain biological operations are still uncertain. DNA computers are not yet programmable or usable by the general public, and research is ongoing to reduce errors, however, errors still exist. Now we have neuromorphic computing. Neuromorphic computing, or computing architecture, and its design principles are based off the human brain. It is a new computing paradigm that offers alternatives to von Neumann's architectures. It is currently under extensive international investigation. The goal of the build of neuromorphic computing is the thinking machines that have hardware designed to mimic biological intelligence. This allows them to function like the human brain. Neuromorphic systems are made from devices that mimic neurons that send information spikes to non-continuous voltages. They also include realistic mechanisms for learning and adapting. However, computation, memory storages, the main happen in the same circuitry, unlike traditional von Neumann computers. The main goal of neuromorphic devices is to have efficient use of space and memory, support for massive parallel connectivity like the brain. They must also have these additional essential features: analog or stochastic programmability, incremental or cumulative programming, interconnection density, on-off ratio, and power consumption. There are two main approaches to developing neuromorphic designs. The first approach is based on analog, very large-scale integration circuits. These have synaptic circuits that integrate into large VLSI spikes neural systems. However, they are silicon-based, so they face the same scaling limits as traditional electronics. The second approach is based on Mefrezite devices. These are nanoscale devices that are passive electronic circuits elements and offer new possibilities for building neuromorphic devices with plastic synaptic connections. Mefrezite devices and resistance switches for memory applications as resistive random access memories. This approach is very attractive due to their CMOS compatibility and their ability to be leveraged in synaptic circuits, neuromorphic architecture, and provide these benefits. Nanoscale passive electronic elements enable neuromorphic architecture with plastic adaptable synaptic connections. They also include technologies such as resistive RAM, phase change memory, spintropic devices, spin torque transfers, and ferroelectronic devices. MEM resistors are not fully understood as their basic physical behavior, and the different ways they switch between resistance states are still being researched. They have the potential to outperform traditional CMOS technology by offering higher density and lower power use. To truly act like the brain, MEM resistors must be able to change their electronical components into small gradual steps, respond to very short electronical pulses, operate at a low voltage, low current, support fuzzy fault tolerant, and flexible types of computing. Now we move on to nanocomputing. Quantum dot cellular nanoatomic, or QSA, is a type of computing technology that does not use transistors. It is considered nanotechnology based on the alternative to traditional electronics. QCA stores information using tiny cells that interact through electromagnetic fields, meaning no electric current flow needs to flow through the system. Each QCI cell contains 4 quantum dots arranged in a square, where each dot can hold an electron. Deposited of these electrons represent the stored information, which is shown in this figure. Nanocomputing continued. Each QNI cell is controlled by these states of its neighboring cells, but not farther away. By using 2 polarization states, +1 and -1, QCA systems can perform logical operations while using much less power than traditional transistor-based systems. QCA systems are extremely regular, meaning that they could potentially be used to use low-cost self-assembly methods. These methods might eventually replace today's expensive top-down manufacturing techniques. A lot of QCA research comes from reversible computing, a field that studies systems where every computational step can be reversed. Reversible computing is a two-way deterministic, meaning you can trace every output back to its exact input. Traditional inputs lose information because their logical operations overwrite previous states. This loss of information also means that the loss of energy as heat. Reversible computing avoids that information loss, allowing the system to keep or reuse some of the energy that would normally be wasted. Nanomagnetic logic, or MNL, is essentially a magnetic version of QCA. Instead of using electrons and quantum dots, it uses tiny magnets that interact through magnetic fields. Because of this, NML is also called coupled computing or magnetic QCA. MNL is more robust than electron-based QCA. Electrons QCA are more sensitive to small changes. Nanomagnets, which behave collectively their spin, are much less affected by structural variation. Nanomagnets use MNL, stable magnets up or down, that represent binary data they process through signals. There are two main types of MNL designs: IMNL, in plane, and PMNL, perpendicular. MNL use early base designs for magnetic charge coupling in the plane of the devices. PMNL is newer design using perpendicular magnetic anisotropy. To date, MNL devices have been proven to meet 5 basic tenets that are considered essential for digital systems. They have non-linear response characteristics deliver functionally complete logic sets enabled by 3 major input gates, signal amplification gain greater than 1 demonstrated by showing feasibility of 1 to 3 fan-out. The output of one device can drive another as the firing fields from individuals. The output of one device can drive another as the firing fields from individual magnets can bias a neighbor. Unwanted feedback is preventable through clocking. Despite all these advantages with nanocomputing, there are still some challenges that researchers are trying to find a solution to. These challenges are moving the external clock to chip onto on-source, moving the external clock source to on-chip, developing reliable magnetic interconnections, developing an electromagnetic interface, improving circuit reliability to fault tolerance, managing thermal noise and fabrication related to imperfections, and nearing neighbor data flow, higher latency, lower processing speed. Now we move on to spintronics, which is also known as magnetoelectronics. It's a new technology that uses spin and magnetic properties of electrons, not just their electronic charge like traditional electronics. When an electron is placed in a magnetic field, it uses its spin polarization, becomes bistable, which can be used to encode the bit logic 0 and 1. The idea of spin-based computing, which is in Boolean logic, gates are created through interacting electronic spins and is the basis of spin quantum computing. A quantum tunnel or junction is made of 2 ferromagnetic layers separated by a thin insulating barrier. Electrons can tunnel through this barrier, creating a small electronical current. In MTJ, each layer has a role. One is a storage layer, and another is another and a reflection layer. In the electronic circuit current, there are 2 types of partial currents, one with a spin up and one with a spin down electron. This figure shows how this process works. MTJs are important because they have a large resistance differences between their magnetic states, even at room temperature, making them easy to read reliably. Some devices use MTJs or hard drives, read heads, MRI memory chips. Some of their advantages are easy to integrate with CMOS, fast data access, and low power consumption, and suitable for both memory and ultra-low power computing. In an MTJ, tunneling current becomes 2 spin polarized as it moves through the barrier layer. This spin polarized current creates a spin torque that can switch the magnetization of the storage layer. The switching direction depends on the direction of the tunneling current. The current can align the storage layer parallel to the reference layer, or it can align with the anti-parallel. Because of this, no external magnetic field is required to flip the bit in an MRAM. SCT performs switching directly through the MT. Here are some advantages of transfer torque: high power efficiency, high fast write speeds, simplifies the process, and enables practical spin-based memory logic. Magnetic random access memory is based on using the direction of magnetization to store information and magnetoresistance information readout. It is designed in 2 different ways, by using MTJs or STT-RAM. Some advantages are non-volatility, extremely high endurance when it comes to reading and writing, high speed operations, low voltage, low power consumption, CMOS compatibility, high density, and scalability, and allows for 3D integration. The following are some major spintronic devices which has been developed. The spin torque domain wall. The domain wall racetrack memory nanomites is a candidate for the next generation of non-volatile memory, and the racetrack is a 3D device which magnetic domains are used to store information in tall columns of ferromagnetic nanowires. A highly spin polarized current passes through the DW, applying a torque moment in the DW, thus shifting the racetrack. The DWs are read by MTJ, magnetoresistive sensing device that can be used to use the spin transfer torque effect. Here's a table showing some spin torque and spin wave majority gates. The spin torque trade aid is similar to the spin-Jordy gate, but uses triangular structures with two inputs and one output. The current in one triangular drives the spin torque switching in the other triangles, enabling electrical spin to conversional instead of simply passing along magnetic signals. All spin logic devices use magnemites to store digital bits and spin currents to communicate information. Applying a voltage to the device generates a spin current that extorts torque of nanomagnets. Switching their polarization, nanomagnets are often arranged in spin majority gates, allowing logic operations without MOS transistors. This property makes LSDAs compact and energy efficient with very low dynamic power and energy delay. Spin wave devices are a type of magnetic logic that use spin collective oscillations or spin waves to transmit and process information. Magnetic films act as spin wave buses with large encoded phases or amplitude waves. Spin wave devices can implement Boolean or non-Boolean logic using volatile or non-volatile states. Here are some advantages that are planned or for future implementations. Use phase amplitude, building logic with fewer elements than transistors, support parallel data process like multiple frequencies, can complement CMOS like tasks like image processing, help reduce interconnection challenges, enhance computational capabilities of circuits, easily cascaded for larger systems. 3D magnetics. 3D ratchets are extended logic from 2D to 3D architectures, improvising density and rather power efficiency. They move nanomagnetic kink solutions between layers without using transistors, and they have potential for 3D microchips but are still experimental. Hybrid spintronics and staintronics. Hybrid spintronics and staintronics use two-phase multiforensics made of piezoelectric and magneto-resistant materials. Applying an electric field to piezoelectric layer creates stress which changes magnetizations and magnetoelastic layer. Both materials cannot be optimized independently to work at room temperature and provide local precise magnetism control. And finally, now we move on to optical and photonic computing. Optical computing uses light or photons rather than electricity or electrons to perform computational tasks. All optical computing aims to fully replace electronic components with optical ones, but so far research is focused on developing optical components that work alongside electronics. Photonic elements include light sources, modulators, optical routers, photonic diode transistors, couplers, and logic gates. They act as optical equivalents of electronic components. Coupling optical components with WDM, or wavelength division multiplexing, allows multiple parallel computations, allowing multiple signals to be processed simultaneously. Optoelectronics photonic circuits for WDM using technologies like arrayed wavelength guides, gyrating, or variable optical attenuators were still the first integrated photonic circuits. The technology is still developing. The recent developments of on-chip non-volatile photonic memory has been developed and offers the potential to replace previous volatile photonic memory devices. Non-volatile photonic memory uses phase change materials, eliminates the need to convert between optical and electrical signals for storage and transmissions, offers potential replacement for earlier volatile photonic memory devices. Ultra-compact all-linear optical logic gates, advanced optical switches, have been realized through nanophotonic fabrication of photonic crystal wavelengths, making them ideal for ultra-fast optical integrated circuits or integration with silicon photonics. Silicon photonics have become a major focus of research for integrated photonic devices recently, as it supports the creation of compact nanowires for guiding light on-chip facilitates integration with silicon-based electronics. In general, combining silicon with integrated photonic devices takes advantage of the availability of large wafers, increasing the ease of handling, thermal cycling, and in high volumes of throughout cost reduction of silicon manufacturing for photonic devices. The benefit of allowing silicon photonic devices are allowing compact nanowires for guiding light on chips, enable integration with silicon electronics, benefits from large wafer availability, ease of handling, and high volume, low cost manufacturing, and offers improved bandwidth, lower latency, higher reliability, and better power efficiency. Despite all these benefits, there are still some problems that come with silicon-based photonics, which are optical absorption issues, low extension ratio modulators, loss in oxide layers, limited optical nonlinearity, difficulty in achieving lasting bulk silicon, electrically injected lasers at room temperature are still challenging, silicon being good for passive photonics but poor for light emission, requiring integration with other materials for sources and detectors. Nanophotonics combine nanocomputing and photonic research and offer a potential alternative opportunity to overcome the fundamental limitations of both electronics and regular photonic circuits. Light confinement is normally limited by structural losses, but metallic nanophotonics can manage losses through engineering, which makes nanophotonics ideal for on-chip applications. Working with light at nanoscale enables dense optical and integrated circuits, solutions to bandwidth and energy dissipation challenges in electronic ICs. The following is a figure showing synergies of speed and size of nanoplasmic chips. Plasmonics is a branch of nanophotonics that uses surface plasmon on SPPS in metal nanostructures. SPPS electronical waves coupled with free electronic oscillations at metal dielectric interfaces with dimensions that's much smaller than wavelengths of light. This enables mixturization beyond current optical devices, which are limited by their larger dimensions. Plasmonics combines the small size of electronics between the size of photonics, acting as a bridge between nanoelectronics and photonic devices. SPPS wavelength detectors act as an interface between electronics and plasmonic circuits. Metallic nanowires, plasmonic wavelengths can carry optical signals and electric currents in the same circuit. However, while SPPs enable fabrication of optical signals, processing devices at sub-blinking scales, this one is done at the cost of losses that make the nanostructure extremely difficult to work with the current devices. While it is known that all photonic quantum devices research is possible in principle, there are still numerous challenges that are being researched. Some of the challenges are below. Photonic interactions are weak, making deterministic quantum operations difficult. Photonic loss occurs due to absorption, scattering, which destroys the information they carry. Amplifiers, commonly used in optical computing, cannot be used because they corrupt quantum information. Building a fully quantum photonic computer requires extensive overhead loss to maintain fault tolerance due to probabilistic operations and photon loss. Hybrid technologies combining photonics with other approaches are more likely the first step towards practical quantum information processing. And that is the end of my presentation. Thank you for watching. Thank you for attending my presentation on subtopics. The topics that will be covered today are membrane computing, and the article is a quick introduction to membrane computing, and DNA computing. And the article for that one is DNA computer, present and future. Membrane computing. Membrane computing is a branch of natural computing inspired from the architecture and the functioning of biological cells. The obtained computing models are distributed parallel devices called P-systems, processing multi-sets of objects in compartments defined by hierarchical or more general arrangements of membranes. Many classes of P-systems were investigated mainly from the point of view of computing power and computing efficiency, also a series of applications. Membrane computing began in 1998 and the finalized research report was published in 2000. By 2003, ISI labeled the original paper as fast-breaking and the field as an emergent research front in computer science. The first membrane computing models were inspired by the structure of a single biological cell. A cell was seen as a hierarchical set of compartments defined by membranes. In these compartments, localized biochemistry took place. This led to a distributed and parallel computing model. Multi-sets of objects, called chemicals, were placed in regions that acted as nodes on a tree. These objects were processed by reactions of biochemical type, and the model expanded using biological ideas such as symport and antiport operations. These operations describe how substances moved across the membrane in real cells. Other extensions came from mathematical and computational motivations. Researchers moved from single-cell population of cells. This shifted membrane structures from simple trees to arbitrary graphs. Some extensions aimed to model additional biological areas, including the brain. The resulting computing devices turn out to be very powerful. They can match the computing power of turning machines with even with restricted features. Some systems can solve computationality, hard problems, such as NP-complete problems, in feasible or polynomial time. This showed that the membrane computing could be computationally efficient. Many applications were later reported across several fields. These included biology, biomedicine, linguistics, computer graphics, economics, appropriate optimization, and cartography. Software tools for simulating P-systems were created. Attempts were also made to implement P-systems in dedicated hardware. The basic classes of P-systems. A P-system contains a membrane structure, a multi-set of objects, and reaction rules, inspired by biochemistry. These membranes form compartments where objectives evolve and the rules act on both objects and membranes together. These elements create the basic setup of a P-system. The membrane computing provides cell-like or tissue-like computing models that process multi-sets inside membrane-defined compartments. These systems are generally distributed in parallel, allowing many processes to occur at the same time. The rules for these objects are provided also localized, acting in specified compartments or on specified membrane. When rules act on an object of membrane, the system's configuration changes, and sequence of these changes form a computation. Once the computation halts, different methods can be used. In theoretical computer science, P-systems are examined for their computing power and efficiency. Often compared to Turing machines, Chomsky grammars, researchers study whether parallelism lets these systems solve difficult problems in a feasible time and explore mathematical ways to define how rules operate and how results are produced. The main evolution strategy in P-systems is a non-deterministic maximal parallel use of rules under a synchronized universal clock. At each step, a maximal multi-set of rules is applied in every membrane, forming the standard execution model. Many variants of P-systems including unsynchronized versions, models that use local bounded or minimal parallelism. There are also deterministic systems, ones that include local halting of each different ways for computations to progress. When a P-system is used to model biochemical processes, it is viewed as a dynamical system focused on its evolution over time. In this context, the key interest lies in deterministic or probability behavior rather than producing specific output. Basic classes of P-systems. The first type of P-system imitates a eukaryotic cell. Its main component is a hierarchical membrane structure forming compartments where multi-sets of objects are placed. In some models, objects can also reside on membranes, like proteins in real life. Objects are usually described by symbols or from a given alphabet, and rules are provided for them evolve in specific compartments or on specific membranes. The most common rules in multi-set writings, U equals U to V, similar to chemical reactions, and transport rules like cis-port and antiport rules move objects in or out of a membrane, while antiport uses simultaneously move one multi-set out and another inside. Rules can be controlled using promoters, inhibitors, or priorities. The membrane hierarchy can evolve by consistently destroying or dividing membranes. Objects can be more than just symbols. They can be strings evolving by rewriting, splicing, or insertion deleting. Objects can also be named value pairs, called conformants, or complex structures like arrays. There are two types of natural-like P-systems. One is similar tissue to P-systems, where neurons are placed at the node of the arbitrary graph containing multi-sets of objects, but they also have a state that controls their evolution. The second type, called spiking neutral P-systems, uses only one type of object called a spike. Information encoded in the timing between consecutive spikes in a number can be recognized as the system eventually halts. All types of P-systems can operate in generative mode, where computation starts from an initial configuration and continues until halting configuration is reached. The result is usually the number of objects in a specific membrane. P-systems can also work in accepting mode, where a number is represented by the multiplicity of an object in a membrane. The number is accepted if the computation halts, which leads to the concept of a P-automaton. Power and efficiency. From a theoretical point of view, P-systems are very powerful. Most classes in Turing complete, even when using simple ingredients such as a small number of membranes, basic rules, or biologically inspired ways of controlling rules. Small universe systems have been built that can simulate any system from a specified class by encoding the system into a universal one. P-systems are also efficient. Many classes, especially those with enhanced parallelism, can solve computationally hard problems, including non-NP complete and even P-space complete problems in feasible, typically polynomial time. This speed up is achieved by trading space for time, often using bio-inspired operations to expand space exponentially in a linear time. Power and efficiency continued. Most studies operations are like membrane division, but membrane creation, membrane separation, string replication, and other operations have been extended to a tissue-like P-systems and spiking neutral P-systems, producing similar results, polynomial solution times to hard problems. Most complexity studies really focus on time as the main parameter, but space complexity also has been analyzed. Applications. As a modeling framework, membrane computing is well suited for handling discrete processes, especially biological ones. It offers several attractive features such as easy understandability, scalability, and programmability. It also enhances compartmentalization and the ability to work with discrete area. Most applications use cell-like tissue like P-systems, and the typical process is a P-system designed to make a model for a specified process, biological, economic, or ecological. Capturing objects, compartments, and evolution rules when a program is used to simulate the P-system, either written or from scratch using software available online. Now we move on to DNA computing. DNA computing, also known as molecular computing, is a new approach to a massively parallel computation based on groundbreaking work by Adelman. DNA computing was proposed to solve extremely hard problems, specifically NP-complete problems where traditional computing time grows exponentially as the problem size increases. It uses specifically chosen DNA strands to represent possible solutions. The combinations of these DNA strands can produce the solution to a given problem. Current technology allows scientists to select the starting DNA strands and filter out the final solution. DNA computing is a new type of computation that uses biomolecular manipulation to solve problems. It also explores natural biological processes as models for computation. In 1994, Leonard Adelman at the University of Southern California surprised the scientific community. He used molecular biology tools to solve a computational problem in a completely new way. The main idea of DNA computing is to encode the data in DNA strands and use molecular biology tools to perform computational operations. This approach is not only novel, but also the potential to outperform electronic computers. DNA computing can be extremely efficient. For example, it may use billion times less energy than an electric computer and store data in trillion times less space. Another advantage is that DNA computing is highly parallel in principle. Billions or even trillions of DNA molecules can undergo chemical reactions simultaneously, performing computations all at once. Today's supercomputers still use sequential logic similar to early computers in the 1930s. Researchers are now exploring completely new computational models, including quantum, optical, and DNA-based computers. Current silicon technology has several limitations: circuit integration systems, clockwork frequency, power consumption, and heat dissipation. The idea of using living cells in molecular complexes as computing components dates back to the late 1950s. Richard Feynman proposed the concept of submicroscopic computers in a famous paper. DNA computing became practical in 1994 when Leonard Adelman solved a small instance of a computationally interchangeable problem using a vial of DNA. By encoding the information into sequences of DNA bases, Adelman demonstrated how existing DNA manipulation techniques could perform a massively parallel random search. There are two main reasons for using molecular biology to solve computational problems. The cubic information density of DNA is extremely high. 1 bit of data can store in about 1 cubic nanometer, whereas other storage media like videotapes require a trillion cubic nanometers for a single bit. DNA operations are massively parallel. A test tube can contain trillions of DNA strands, and the operation performed affects all strands simultaneously, allowing many computations to occur at once. DNA is the main information storage molecule in living cells. Over billions of years, evolution has refined both this molecule and the highly specific enzymes that can copy DNA or transfer its information to other molecules. Instead of using traditional electronical impulses to represent its information, DNA computers use the chemical properties of DNA molecules. It processes information by examining how these molecules combine, interact, or grow in specific patterns. A single strand of DNA works like a string made from 4 symbols: A, G, C, T. Mathematically, this gives us a 4-letter alphabet, A, G, T, T, for encoding information, which is more than sufficient since an electronic computer only needs 2 symbols, 0 and 1, to do the same. Operations that can be performed on DNA strands, proposed models of DNA computation, are available based on various combinations of the following primitive bio-operations: annealing, which bonds together single-stranded complementary DNA sequences; melting, which breaks apart double-stranded DNA into its single-stranded complementary components; amplifying, or copying, is the process of making many copies of DNA strands using this polymerase chain reaction. And this figure shows how that occurs. Separating the strands by using length of the technique called electrophoresis that uses possible separation strands of length. Extracting those strands contains given patterns of substrings by using affinity purification. Cutting DNA is when you use double strands at specific sites by using commercially available restriction enzymes. One class of enzyme is restriction endoclesis. Will recognize a specific short sequence of DNA known as a restriction site, and any double-stranded DNA that contains that restriction site is cut by the enzyme at that location. Another is litigating, which pastes DNA strands, which is compatible with sticky ends using DNA languages. Substituting, which you substitute or insert DNA sequences using PR site-specific oligonucleotides, mutein-genesis. Marking a single strand through hyperbenation includes attaching complementary DNA sequences to make a single strand. When this happens, the strand becomes a double-stranded. The reverse process on marking is done through dentering, which separates 2 complementary strands. Destroying marked strands can be done by using exon cleasis or by cutting down marked DNA with a restriction enzyme and then removing the intact strands through gel electrophoresis. And detecting and reading involves checking whether a test tube contains at least one DNA strand. If it does, the answer is yes, and if not, the answer is no. To read the actual information, PCR can be used to amplify any DNA present. After amplification, a process called sequencing is performed to determine the exact genetic sequence, which represents the final solution. The following is an example of DNA binary code. DNA computers work by encoding problems into the language of DNA using 4 bases, A, T, C, and G. This 4-base system allows any problem to be represented along a DNA strand. Every possible DNA sequence is needed for computation can be chemically created in a test tube, creating trillions of different strands. A few years ago, researchers at Weizmann Institute of Science in Rehovot, Israel, introduced a programmable molecular computer made from enzymes and DNA molecules instead of silicone and microchips. According to Edu Shapiro, the device uses DNA input as a fuel to operate. This molecular computer is extremely fast, performing 330 trillion operations per second, which is over 100,000 times faster than the fastest traditional personal computer. While a desktop PC is designed to perform one calculation at a time very quickly, DNA computers can generate billions of potential answers simultaneously. This makes DNA ideal for fuzzy logic problems with many possible solutions. In the future, some researchers speculate there could be hybrid machines that use silicon processors for normal tasks, but DNA coprocessors for specialized problems. The main question today is whether challenges in DNA computing practical controllable. They're reliable or insurmountable, designing onto oligonucleotides and molecular biology protocols for error-tolerant computing may be difficult. Success may vary on compiling collections of oligonucleotides and developing protocols that allow DNA computing to work reliably. Current protocols were not originally designed for computing applications, and it may be present technology we cannot fully characterize DNA chemistry and physics well enough to build DNA computers. To finish this presentation, here's a list of advantages and disadvantages that come with DNA computing. Some advantages. They can perform millions of operations simultaneously, can generate a complete set of potential solutions, and conduct large parallel searches, efficiently handle massive amounts of working memory, inexpensive to build using common biological materials, providing distinct memory block that encodes bits, and use one template strand as a memory block, allowing its components to strand and serve as another memory block effectively. Some disadvantage. Generating solution sets for even relatively small problems may require a large amount of DNA, making it impractical at times. Here are many empirical certainties such as actual error rates, developing optimal encoding techniques, ability to perform bio-operations conveniently in vitro, and DNA computers cannot fully replace traditional computers, and they are not easily programmable. Thank you for attending my presentation.